Alright guys, today we are working in Chapter 4, Section 6. Now here's the good news. The good news is that Chapter 4, Section 6 is nothing new calculus-wise. Chapter 4, Section 6 is the synthesis of a whole lot of concepts we have been talking about throughout the semester. So we're going to put together all of the discussion about derivatives, second derivatives, all the things that those two items tell us, and we're going to use that in conjunction with all of the items and concepts we know how to find from algebra and trig, perhaps, and we're going to use all of this information to graph by hand. It's called curve sketching. Okay? We're not going to be as good as software, of course, but we're going to be able to hit the high points, be able to graph by hand the important stuff to get a good picture of what's going on. So there's a lot of intuition that'll come with this eventually. So you want to practice this a lot. I'll do a handful of examples today. Again, nothing new, but we're going to do all of the stuff we've been doing for a single function: maximums, minimums, concavity, inflection points, along with all of this stuff from algebra like asymptotes, x-intercepts, y-intercepts, domain, range, maybe symmetry, and we'll get a pretty good graph. So let's see what happens here. All I'm doing here is examples. Again, there's no new theorems, no new concepts. We're just putting it all together. Alright, so I'm going to start off with a one that's on the easier side. I mean, none of these are trivial, but I'll say this is definitely on the easier side. So let's see here. I'm going to start with a nice cubic. Let's see, f of x equals 1/3 times x cubed minus 2x squared plus 3x. Okay, that's just a pretty nice cubic equation, polynomial. So you always want to start recognizing a few key things. The first kind of things I think about when I see a function is domain specifically, and then in range as well. But domain is kind of the first thing that pops in my head. And what I recognize here is that this is a nice polynomial. It has rational coefficients. You know, we're not dealing with anything crazy here. Polynomials are going to have domain equal to all real numbers. So that means I don't have any asymptotes to worry about, and this is going to be just a nice smooth curve. You know, polynomials are nice to work with. So the first thing I recognize here is the domain is all real numbers, and it turns out the range is going to be all real numbers as well. Now we just want to pretty much actually, you know, one more thing I'll note before we jump into calculus. From algebra class, we know that the leading coefficient test helps us out as well. Okay, the leading coefficient test tells us what the end behavior of this will look like. Okay, we had the leading coefficient test. It only worked with polynomials, but it says look at the leading coefficient. In this case, it's a 1/3, and consider the degree of the polynomial. This is a third degree polynomial. So we'll say the leading coefficient is 1/3, and the degree is equal to 3. And so the leading coefficient test, and if this doesn't ring a bell, maybe pick up a college algebra book and look at it. But the leading coefficient test tells us that this function is going to be rising to the left and, falling to the left and rising to the right. So we indicate end behavior kind of like this. If you have like a little graph here, we know that it's going to look something like this as far as end behavior is concerned. It's going to be rising far off to the right and falling far off to the left. Now what happens here in the middle, that's what the rest of this discussion is going to be about. But the end behavior looks like this. Okay, so now let's jump into the calculus and see what's going on here. Okay, so the first thing you want to do, at least that I would do, is find the first derivative and then find the second derivative. Because we're going to need the first derivative to figure out increasing versus decreasing behavior, relative extrema, and the second derivative gives us concavity and inflection points, and we can also find relative extrema if we so choose, using the second derivative. So let's see here. This derivative should be quite easy. So f prime of x equals, okay, power rule here just says that it's 3 times 1/3 times x squared. So 3 times 1/3 just multiplies together to 1, leaving us with x squared. Okay, the power rule here says we take the derivative of x squared, ends up being 2x. 2x times -2 is -4x. And of course, the derivative of 3x is just 3. Excuse me. Okay, so let's see here. Yep, x squared minus 4x plus 3. Now I'm going to go ahead and find f double prime while I'm here. F double prime of x, just differentiate all over again. So the derivative of x squared, of course, is 2x, and the derivative of -4x is -4. Okay, now we need to do our analysis of the first derivative and the second derivative. Now remember, the first derivative, that gives us critical points, that is possible extrema, and then we can use the first derivative to also find increasing and decreasing intervals, and then we can use the first derivative test to find the relative extrema. So let's find the critical points first. Now recall, the critical points are points for which the first derivative either does not exist or is 0, but critical points must be in the domain of the original function. Now this is actually pretty nice, because all I have to do here is solve this quadratic. Because x squared minus 4x plus 3, that is a polynomial that has a domain of all real numbers. So there is no points for which the first derivative, f prime, is undefined. So that means this function, f of x, is differentiable everywhere. So now to solve that, I can use the quadratic formula, but I think that's probably overkill. I think I can factor that, right? We could say that's x minus 3, it looks like, times x minus 1. And so we could say either x minus 3 equals 0, or x minus 1 equals 0 by the zero factor theorem, which tells me my critical points are x equals 3 and 1. So there are my critical points. They are the solutions to f prime of x equals 0. So these are my critical points. So if I have a relative extrema, it must occur at one of these points, or they could be two. Could be one, could be a max, one could be a min. They could both be relative mins and maxes, depending on how the function plays out. But my relative extrema have to be in this list right here. Okay, so in order to find which one is a minimum and which one's a maximum, we'll actually first figure out where we have increasing versus decreasing behavior, and then we can use the first derivative test to find those extrema. Now what I like to do here is just, at least to start with, is sketch a real number line. So my domain is all real numbers. I'm going to use these critical points to divide up my domain. So I have 1 and I have 3. So notice if I have those two critical points, then that divides my domain, which is all real numbers in this case, into 3 distinct sections. So I have the interval from -infinity to 1, from 1 to 3, and from 3 to positive infinity. So I'm going to use those intervals and figure out where my function is increasing or decreasing. Because on this interval, it's going to have all of the entire same behavior. The entire thing is either going to be increasing or decreasing. This middle interval here, the entire thing is either going to be increasing or decreasing. And then over here as well, the entire thing will be increasing or decreasing. So let's see here. Let's make out this chart. Let's see. So we have our intervals first. Let's see. We had negative infinity to 1. And these are open intervals, very important. We're never going to use closed intervals here. 1 to 3. Because those are critical points, which probably is going to mean there's a horizontal tangent line. If there's a horizontal tangent line at that point, it's not increasing or decreasing at those points. So we use open intervals. Then we want to pick a test point from each of those intervals. Now again, you can pick any test point you want in that interval. The result that you get from the process we're about to complete will be the same no matter which test point you pick from that interval. So, like, I could do, say, -2. That's easy. I could do, say, +2 there. And I could do, say, +4 there. But I could also pick 5 over here. I could pick 1,000,000. It would be the exact same result. Here I could pick 2.5. I could pick 1.5. I could pick 1.99. As long as in that interior of that interval, which it's an open interval, so it has to be in the interior, then we are good. Now we need to evaluate f prime at those test values, and we're looking for the sign of f prime. So when we go to look at an f prime, which is right here, what happens when we plug in a -2? Okay, well we have -2 squared, that's +4, but then we have +4 plus 3, that's +7. Okay, that's +7, but then you have -2 times -4, so that's +8. So we have a positive plus a positive plus a positive, so I think the result is positive. Now what about +2? If you plug in a +2, you have 2 squared is 4, but 4 minus 8 is -4. -4 plus 3 is -1. So the result is negative. And then what about when we plug in a 4? Again, we're looking at f prime of 4. That would be 16 minus 16 plus 3. So the result is +3, but we're only concerned with the sign. Now the result, the conclusion, or the result, is that we are increasing right here. We are decreasing on that middle interval, and then we are increasing over here again. Where your first derivative is positive, your original function is increasing. Where your first derivative is negative, that is where the original function is decreasing. Okay? Now, the first derivative test, we can use that now. Because the first derivative test says all you have to do is observe where your function is changing from increasing to decreasing or vice versa. And if that change happens at a critical point, there's two possibilities. If you change from increasing to decreasing, like we do here at a critical point 1, we change from increasing to decreasing, then that critical point is going to be a maximum. I should say a relative or local maximum. Relative max is going to be at 1 comma something. I'll find that something in just a sec. And then the first derivative test otherwise tells us if you change from decreasing to increasing at a critical point, then that results at a relative minimum. So 3 comma something is going to be where the relative minimum occurs. Now, why does this make sense as far as the first derivative test is concerned? Let me draw a picture real fast. Let's say your function is decreasing. That means it's going like this, going down from left to right. But let's say you hit a critical point, and then all of a sudden your function starts increasing. So you're decreasing, 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 critical point, which means there's going to be a horizontal tangent line, and then you're increasing after that. Or actually, that would be an undefined point there, rather. But that is possible as well. So there, the way I drew the picture, that there is not a differentiable point. That's a cusp. Maybe it's not. Yeah, that's the way I drew it. It's too sharp there. But that is a minimum because we change from decreasing to increasing at a critical point. Likewise, let's say your function is increasing, 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 increasing. You reach a critical point, and then you're decreasing after that. Well, that would lead at a relative maximum. So that's where this comes from. Because we switched from increasing to decreasing, that's what's going on. You're going up, 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 up. Then you have a horizontal tangent line. Then you go down after that. Therefore, that is a relative maximum. Okay, so that's why the first derivative test works. It makes sense if you consider a picture. Now, let's find the y values for our relative maximums. So that's going back to the original function here. Let's see here. If we evaluate f of 1, you would have 1 cubed divided by 3, so that's 1/3. Okay. Minus 2 times 1 squared, so minus 2, plus 3 times 1, so plus 3, and you get 1 1/3, so 4/3. Okay, so we have a relative maximum at 1, 4/3. Okay. And then our relative minimum occurs when x equals 3. So let's substitute in a 3 into f. So that is 3 cubed, so that's 27, divided by 3, you get 9, minus 2 times 3 squared, so that's minus 2 times 9, minus 18. Then you have plus 3 times 3, so plus 9, you get 0. So there are 2 points on our graph, and those are both relative extrema. So that's a good start. We found where we're increasing and decreasing, and we use the first derivative test to find the relative extrema. There are no other relative extrema. These are the only options. But now let's analyze the second derivative so that we can talk about concavity. Okay, so let's find our possible inflection points. So kind of like we found critical points with the first derivative, let's find the possible inflection points by setting f double prime equal to 0. So here's f double prime over here, set it equal to 0 and solve. Also, we're also considering where f double prime might not exist. But just like f of x, excuse me, just like f prime of x, and just like f double prime now, these are all polynomials, so they exist for all real numbers. So we say the domain of f is all real numbers, the domain of f prime is all real numbers, and the domain of f double prime. That means that f is differentiable everywhere, and f is twice differentiable everywhere. So we solve for x here and get x equals 2. So x equals 2 is our only possible inflection point, but let's verify that by creating a graph. Just like we made a graph up here, by dividing the real number line according to our critical points, we're going to divide the real number line according to our possible inflection points, which there's only one. So we have 2 intervals. we have the interval from negative infinity to 2. And we have the interval from 2 to infinity. Again, open intervals. We pick a test point from each interval. Alright, so let's see. There's like a 0 works over on the left one. And say, let's pick 4 over there. But now we're going to consider the sign of f double prime at those test points. So sign not of f prime, but f double prime. So let's see. Here's f double prime over here. What happens if you plug in a 0? You get negative 4. So the result's negative. What happens if you plug in a 4? You get 8 minus 4, so you get positive 4, a positive number. Now the result is that when your second derivative is negative, the original function f is concave down. But where f double prime is positive, the original function f is concave up. So now we know about concavity, and this right here tells us that since we changed from concave down to concave up, at this point x equals 2, then x equals 2 is an inflection point. So that indeed is an inflection point. Now, I suppose we should say 2 comma what? So 2 comma something is an inflection point. Let's figure that out by evaluating f of 2. So 2 cubed is 8 divided by 3 minus 2 times 2 squared, so minus 8, plus 3 times 2, so plus 6. I get 2/3. So here's our inflection point. 2 comma 2/3. So I think we're well on our way here. We have talked about the first derivative, and we found increasing and decreasing intervals, and we found relative extrema. We looked at the second derivative, and we found inflection points and concavity. Now we can verify our first derivative test using the second derivative test. Actually, let's go ahead and get that practice in. Okay, the second derivative test says if you evaluate f double prime at a critical point, so our critical points are 3, and our critical point, our other one is 1. If you evaluate f double prime and get a positive result, then that critical point is a minimum. If you evaluate f double prime and get a negative result, then that critical point is a maximum. So let's see, what's f double prime of 3? Well, it's 2 times 3, which is 6 minus 4, is positive, so 3 should be a minimum, which it is. So like we just double checked ourselves. So the second derivative test says 3 is a minimum. Now what's f double prime of 1? F double prime of 1 is 2 times 1 minus 4, which is negative 2, less than 0. Therefore, by the second derivative test, 1 is, oh, I shouldn't say, I said this backwards. I should say max occurs at 1. So I should fix this up here too. 3 is where a maximum occurs. It's not the actual maximum value. The maximum value is the y value. We should say min occurs at 3. That's better. Okay? So we just double checked ourselves. So the second derivative test, just to be clear, the second derivative test like the first derivative test, is a way for us to find extrema. Okay, even though we usually find increasing versus decreasing with the first derivative and inflection concavity with the second derivative, the first derivative test and the second derivative test give us relative extrema. Okay, that's a lot of times people get that mixed up, thinking the second derivative test tells you about concavity. Now, the second derivative does tell you about concavity, but the second derivative test is just another way to find relative extrema. Now, let's see about putting all of this together. So I'm out of room here. Actually, I'll use this little space right here and see if it shows up nicely. So let me draw a graph, a sketch right here in the middle. Okay. So let me draw just an axis here. Again, this is a sketch. Maybe we'll look at a software rendering of it in just a minute. But of course, we have our x-axis, we have our y-axis. Now let's plot our points that we know. Okay, we know that at, let's see, what do we know here? We know that at 3, 0, there's a relative minimum. Okay, so let's plot 3, 0. Let's say, okay, we need some scale here. So let's say 1, 2, 3, like this. Okay. Now we know at 3, 0 there is a relative minimum. So there's 3, 0. Okay. We know at 1, 4/3 there is a relative maximum. So 4/3 is about 1 1/3. So that would be about right there. That's a maximum. So we'll say local max, and that is a local min. Okay. Now, what do we know about, oh, we haven't done the algebra yet, but the algebra is pretty easy, I think. How do you find the x-intercepts? And how do you find the y-intercept? Let's do y-intercept first. Y-intercept is found by evaluating f of 0. In this case, what's f of 0? Well, in this case, it is 0. So we know there's a point on our graph. There's a y-intercept at the origin, which means there's also an x-intercept at the origin. Now, how do you find the x-intercepts? You say f of x equals 0 and solve. So let's do that down here. F of x equals 0. That's just pure what you do in college algebra over and over again. Find x-intercepts. They're called zeros, or they're called roots. So we could say, okay, we're running out of room here, but this is not too hard. That is, let's see, 1/3 x cubed minus 2x squared plus 3x. We can factor out an x. So we could say that, oh, I did that wrong, equals 0. Now let's say we factor out an x. We could say that, and what else can we do? I want to get rid of that fraction. So what if we multiply everything by 3 and then pull out an x? So we would have, let's see if I can do that in my head real fast. So we would get rid of that fraction. We would pull out an x, and we'd be left with x squared. We would multiply by 3 and get negative 6x squared, but pull out an x, and so you get negative 6x. Then we would multiply by 3, get 9x, but pull out an x, and we would get 9. Okay? Now, that equals 0, of course, still. Now, we're trying to solve that, so let's factor this. I think that factors pretty nicely. That factors is x minus, x minus 3 squared. This is actually very helpful because, okay, this factors is x times x minus 3 squared equals 0. Now, this is actually, if you remember your discussions from college algebra, what does this tell us right here? This tells us actually what we know already. that there's an x-intercept at 0, which we already know about, and there's an x-intercept at 3, which we already know about. But what does this specifically here tell you? That we have x minus 3 squared. Remember that idea of multiplicity? Multiplicity means that this factor right here is repeated twice. We have a multiplicity of 2. It's x minus 3 times x minus 3. Now, do you remember what that means? It means that the graph turns around but doesn't cross the axis. So it means that f touches but not cross at that point, which makes sense because it's a local minimum. So I'm not crossing the x-axis right here. I'm going to touch it and turn around, which makes sense if it's a local minimum. So our algebra here is verifying the calculus and vice versa. Now let's talk about increasing and decreasing. We know this is our end behavior here. So we know we have to be going like this. Let's see here. Let's get a new color here. We have to be going, we're increasing by the first derivative, we're increasing from negative infinity to 1. Okay? So we're increasing. We hit this point, which we know about, and we're increasing all the way to 1. And then from 1 to 3, we're decreasing. So we're decreasing. Oh, that's not good. We're decreasing. We touch, but we have to turn around because of the multiplicity of 2 there. Now I should make that more clear. Bounce and turn around. And now we're increasing after that because our first derivative test says we're increasing like so. So there we go. Now let's check our concavity. Our concavity says that we are concave down from negative infinity to 2. So yeah. Okay, now I'm doing this right here. Let's see here. I should make it maybe a little more curved. Now I'll do that actually. Let's make it a little more. Oh, I forgot. That's going to erase that right there. I won't do that then. That's fine. I should make it though just a little more curvy. A little more curvy. So it's obviously opening downward like so. Okay. But then what happens at 2? It changes to concave up. So now it has to be kind of like opening upwards. And I think that there we go. Opening upward from 2 to infinity. So I need to draw that inflection point. There's an inflection point right here. There was the maximum right there. There was the minimum right there. And that was the inflection point. So there you go. There is our total graph. We have our inflection points. We verified our concavity. We have our local extrema. We have our end behavior right. And there you go. I mean, that's a lot of work, but that's like the synthesis of most everything we've been doing this semester, at least in Chapter 4. The one thing that we didn't do here because it wasn't necessary is really evaluating the formal limits at infinity. What I mean by that is evaluating these two things. Let's see here. The limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. Now we'll do that more in a formal sense in other examples, because here the leading coefficient test does that for us, since this is a nice polynomial. But the leading coefficient test doesn't work if you're not working with a polynomial. So we'll have to do this extra step in some of the other examples. Okay, but that's like the one additional step that we didn't do because we had a shortcut from algebra class. But we'll do those on some of the next examples, perhaps. Okay, so let's see. There's the and I hate to say this, but that is definitely an easier derivative to work with, easier second derivative. That was a pretty straightforward function. It turned out that the critical points were nice whole numbers. The inflection point was a nice rational numbers. So it all worked out pretty nice for us. It won't always work out so nice as far as having nice, pretty numbers, especially like if you're working with a logarithmic function or if you're working with a trig function, you'll have pi's and stuff like that involved. Now, I haven't been keeping track of the time, so if I had to guess, that's probably at least 30 minutes, if not longer, worth of work. So let's do maybe one or two more. I'll try to pick some that are representative of what we'll be doing. But we're just going to repeat this process over and over again. We want to find first derivative, do the analysis, second derivative, do the analysis, so forth and so on. Let's do a trig next, a trig function, and we'll see what happens here with trig. So I picked one out of the log. We'll see how it turns out. I picked f of x equals, what was it? It was 2x minus 4 cosine x, and we were restricting our domain to 0, 2 pi, and we were including those endpoints. Okay, so this is our function. We want to make a complete graph of this function over this specific domain. Now, of course, with the trig functions, we're usually going to restrict our domain because they're periodic in nature. So we're usually going to say 0 to 2 pi, but there could be other restrictions on the domain. So first step, at least in my book, would be to find the first derivative and find the second derivative. So let's see here. F prime of x equals, the derivative of this term and the derivative of that term individually. So we have 2. And the derivative here would be negative 4 times negative sine x, so plus 4 sine x. Okay. What about the second derivative? So that would be f double prime of x. Okay. The derivative of 2 is 0. The derivative 4 sine x is just 4 cosine x. So there's our original function, first derivative, second derivative. So let's first do the analysis on the first derivative. So we can find increasing versus decreasing behavior. And of course we can find extrema if we choose to use the first derivative test. Okay, so let's see here. We are looking at f prime of x to find critical points. F prime of x equals 0. Okay, f prime of x equals 0. So we're trying to solve 2 plus 4 sine x equals 0. If we subtract 2 from both sides and then divide by 4, we're actually looking at sine x equals negative 1/2. Negative 2 over 4, negative 1/2. So we need to find the solutions to this. So what does x equal? Okay, well, think about your unit circle. Maybe I'll do a quick sketch here. If we have this, okay, we want to know where sine equals negative 1/2. Now, we all know that sine equals positive 1/2 right there, because the coordinates there are root 3 over 2, comma 1/2. Now, that's positive 1/2. So if we want, and that's, of course, the y value is where we're looking for sine. So if we want the if we want sine of but a negative 1/2, then we know there's an angle over here where the coordinates are negative root 3 over 2 and negative 1/2. Okay, now what is that angle? Well, you could call it negative pi over 6 if you wanted to, but negative pi over 6 is not in our domain. So what is the coterminal angle that you find by considering this way instead? Okay, so essentially you have to ask yourself, what's 2 pi minus pi over 6? And I think the answer you get is 11 pi over 6. Okay, 11 pi over 6 is one of our solutions. Now the other solution is, okay, we know that there's going to be 2 angles in 0 to 2 pi where this happens. There's also this angle over here. Okay, the coordinates of that point on the unit circle are going to be, oh, you know what, I said that was negative. That's positive right there. Sorry about that. I don't know where my brain is this morning. That's a positive root 3 over 2. The y value is still negative. Now over here, both of those, in the third quadrant, it's negative root 3 over 2 comma negative 1/2. And so the question is, what is this angle right there? Well, 180 degrees is pi, so it's essentially pi plus pi over 6. Pi plus pi over 6 ends up being 7 pi over 6. So 7 pi over 6. So those are our 2 critical points. Okay, so now to build out our chart, we are going to use these and divide up our domain. So our domain here is not all real numbers, it's 0 to 2 pi. So we need to divide up the interval 0 to 2 pi, but divide it up according to 7 pi over 6 and 11 pi over 6. So we have 3 test intervals to work with. Okay, so we first have our intervals. We said from 0 to 7 pi over 6. We then have from 7 pi over 6 to 11 pi over 6. We then have from 11 pi over 6 to 2 pi. So those are our 3 intervals. Now we need to pick a test point from each of those intervals. Let's try to pick nice ones. So essentially we have from 0 degrees or 0 radians over here to 7 pi over 6 radians. I'll pick a nice one. Let's pick pi. Okay. What's a nice one between 7 pi over 6 right here and 11 pi over 6 right there? I think 3 pi over 2 is nice. Oh, but here's a little issue. You know, we're looking at what's between right here. There's not really a great angle. I mean, I could say, I guess pick one. I mean, I just need to pick a number. I was trying to pick one so that I could do it in my head. Now, you could certainly use identities to do this in your head, but let's pick. Oh, what's a number, a test value between 11 pi over 6 and 2 pi. Oh, I'm just going to pick one using my calculator real fast because I'm not going to bother with trying to use identities to do it by hand. So let's see. 11 pi over 6 is approximately 5.75 and 2 pi is approximately 6.28. So let's just pick 6. And we'll just use our calculator to evaluate the sine of f prime at 6 for that time. But we'll be able to do these other ones in our head. So now this is the sine of f prime. So let's go to f prime and plug in a pi. Okay, what's sine of pi? Okay, sine of pi is 0. So you have 4 times 0 is 0, 2 plus 0 is 2. So it's positive. Okay. What about 3 pi over 2? Again, we're going to f prime here. So sine of 3 pi over 2 is this quadrantal angle down here. It's -1. So you have 4 times -1 is -4. 2 minus 4 is a negative result. Now, I'm going to use my calculator here. I'm just going to say 4 times the sine of 6 plus 2, and we get a positive result. Okay, positive result there. Now let's see here. What does that tell us? That tells us that we are, so the result, we are increasing on the first interval, we are decreasing on the second interval, and then we are increasing on this third interval. Here it just so happens that we're alternating. It won't always be the case, but here we are alternating. I should say that this, I forgot to mention that when we were doing our critical points, that f prime is defined for all real numbers. So there are no critical points that are due to the first derivative not being defined. Okay, that happens a lot of times with rational functions. Maybe that'll be the last example we do. We'll do a rational function like when you have an asymptote. So the only critical points we had were critical points due to the first derivative being 0. Okay, now that is increasing versus decreasing. So now we can actually talk about the first derivative test. Because the first derivative test says that if you switch, if at a critical point, you switch from increasing to decreasing, that leads to a relative max. So we're going to have a relative max at 7 pi over 6. Because we switched from increasing to decreasing. So 7 pi over 6, comma something. And we're going to have a relative minimum when we switch at a critical point from decreasing to increasing. So at 11 pi over 6, we're going to have a relative minimum. Now, let's figure out what those y values are. Now, again, to find the y values, you always have to go back to the original function. So let's look at 7 pi over 6. Oh, this is not going to be pretty. Actually, I might need to give some more room to my y values. So let's see here. If I evaluate f at 7 pi over 6, I'll have 2 times 7 pi over 6. So that's going to be 7 pi over 3. Oh, I'm going to have to write this down. I can't do this in my head. I don't trust myself to do it in my head all of a sudden. So that's going to be 7 pi over 3 minus 4 times cosine of 7 pi over 6. Now, the cosine is the x value of 7 pi over 6. So that's negative root 2 over 2. Yikes. So negative root 2 over 2, that's going to result, we have 7 pi over 3. Then we're going to have plus 2 square roots of 2. That's not pretty. So 7 pi over 3 plus 2 square roots of 2. That is the y value. Now, when we start to graph this, I'll get a decimal approximation of that. Now, let's find the y value when we evaluate at our relative minimum, 11 pi over 6. So we're going back to the original function, f of 11 pi over 6. So that's going to give us 11 pi over 3 minus 4 times the cosine of 11 pi over 6. Now the cosine of 11 pi over 6 is the x value here, so that's just root 3 over 2. So 4 times root 3 over 2, that's going to give us 11 pi over 3 minus 2 square roots of 3. Oh, you know what? I said the wrong thing over here. I misread I misread my terrible handwriting here. I wasn't thinking. All right, back up just slightly. That is a square root of 3. So let me fix this. Square root of 3. Okay. So that means this over here needs to be a square root of 3. Sorry about that. I get on to my daughter whenever she can't read her own handwriting and writes the wrong thing down, and I just did the exact same thing myself. So that's a square root of 3. Okay, that's what I get for having that sloppy or trying to write too small there. Okay, so now we have minus. Okay, it was 11 pi over 3. Crisis averted. 11 pi over 3 minus 2 square roots of 3. Okay, so there are our extrema. 2 extrema on this interval. So we've done all we can do with the first derivative at this point. Now let's look at the second derivative. That'll give us our possible inflection points. Okay, so possible inflection points. That is when we set f double prime equal to 0 and solve. This is going to, f double prime of x equal to 0 and solve. Okay, so f double prime is here. That is 4 cosine x equals 0. We can divide both sides by 4, and this is all we have to solve. That's a lot easier to work with. So looking at 0 to 2 pi, when is cosine equal to 0? Well, that's easy. That's just at pi over 2 and 3 pi over 2. Okay, pi over 2 and 3 pi over 2. Those are the quadrantal angles, 90 degrees and 270 degrees. They have an x value of 0. Okay, so now these are our possible inflection points. Now I should say we're also potentially looking for points where 4 cosine x is not defined, but that is defined for all real numbers, so it's differentiable at all real numbers. So f, we say, is twice differentiable for all real numbers. Okay, so now I need to make this exact same chart, except with these new points, and the results are going to give us concavity instead of increasing versus decreasing. So here are our intervals. Now again, we're dividing up the domain from 0 to 2 pi, so we have 0 to pi over 2. We then have pi over 2 to 3 pi over 2. And then we have from 3 pi over 2 to 2 pi. 3 test intervals. Let's pick some test points. Let's pick some nice ones. Okay, pi over 2 is 0 to pi over 2. Let's pick pi over 4. That's a nice one. Here, let's pick pi. That's a nice one that lives in there. Over here, let's pick 7 pi over 4. That's a 45-degree angle increment. I like that one. Nope, not over 2. Over 4. 7 pi over 4. Okay. Now we need to evaluate f double prime at these. I should say, I tend on these trig functions, I pick nice test points that I can use the unit circle for. It doesn't matter. You can pick any number here. Like, you could pick, okay, what's the approximation of pi over 2? Pi over 2 is approximately 1.57. So you could pick a test point of 1 and use your calculator to evaluate the test f double prime at 1. So sine of f double prime. It doesn't matter if you pick nice points here. I'm doing them so I can do these in my head, because I know that that if I'm looking at here, f double prime is 4 cosine x. It's really easy to take cosine of pi over 4. It's root 2 over 2. So I have root 2 over 2 times 4. That's clearly a positive. If I look at cosine of pi, well, cosine of pi is negative 1. So negative 1 times 4 is negative. And if I look at cosine of 7 pi over 4, well, the cosine of 7 pi over 4, that's a 45-degree angle over here in the third quadrant. All you really have to remember is that cosine is positive in the fourth quadrant. Okay, over here in the fourth quadrant, cosine is positive. It's actually going to be root 2 over 2. So root 2 over 2 times 4 again is just going to be a positive. So there we go. So what is the conclusion or the result? Is that we are concave up here down here and up here. Where f double prime is positive, we're concave up. Where f double prime is negative, we're concave down. So there is our concavity. Now, this is going to lead to 2 inflection points. So this tells us that when we change from concave up to concave down, there's an inflection point. So we have an inflection point at pi over 2 comma something. And we're switching from concave down to concave up at a possible inflection point. So we're going to have 2 inflection points. Now, to find those inflection point y values, we have to go back to the original function. So let's see here. If we plug in, I'm going to have to do a little scratch work again. 2 times pi over 2. Well, that's not bad. That's just pi. But minus 4 times cosine of pi over 2. That's root 2 over 2. Okay. Oh, not root 2 over 2. Sorry about that. I was thinking pi over 4. It's pi over 2. Cosine of pi over 2. That's not bad. That's just 0. So it's pi. I was thinking that was going to be tough for no reason. Now, what about 3 pi over 2? Okay, if I plug in a 3 pi over 2 back into my original function, I would have, let's see, 3 pi minus 4 times the cosine of 3 pi over 2. Cosine of 3 pi over 2 again is 0, so it's 3 pi minus 0. So there we are. So there are our inflection points. Not possible anymore. Those are inflection points. Okay. What else can we do? What else can we do? We don't have to really talk about end behavior here because we have a restricted domain. So that's nice. We don't need to worry about the limits at infinity. So what about x-intercepts? Oh, x-intercepts here, those are not going to come easily. Okay. Equations like this, like if you want to find the x-intercept, you set f of x equal to 0 and solve. That is not going to, there's not an easy way out of this equation here. So to find x-intercepts, I'd want to solve this equation. I would want to solve, let's see, f of x equals 0. Thus, I want to solve 2x minus 4 cosine x equals 0. There is not an easy way to solve an equation like this. So like we need to solve this. 2 cosine x equals x. Okay. Sometimes you get lucky, but so I'm not going to worry about the x-intercepts right now. Essentially you would need to approximate them using Newton's method, using the intermediate value theorem, using a graphing calculator. But the whole point here is not to use a graphing calculator, so I won't do that at this point. I think one, let's see, let's do the y-intercept though, I suppose. The y-intercept is when you evaluate this at 0. Okay, that's important here. What happens if you evaluate f of 0 to get a y-intercept? You get 2 times 0, which is 0, minus 4 times 1. So that's negative 4. So that tells us something good, that there is a, that's nice that we have a y-intercept at negative 4. Okay. Anything else? So we have a y-intercept, x-intercepts, not so easy to come by. I think we'll be fine without that. Let's start graphing this and see what happens. Let's see here. Let's see about getting an axis going. Actually, I'm going to draw it over here because we're only concerned with 0 to 2 pi. So we only need, essentially, maybe the first 2 quadrants. X and Y. Okay. So we found that we had an x-intercept. Over here at 0, negative 4. So negative 1, negative 2, negative 3, negative 4. Now I'm going to label our x-axis in terms of pi's, but I'm going to label my y-axis just Actually, you know what? I should probably not count by ones. I should probably count by something higher than that because some of our y values are kind of big. We have, let's see, we had a y value here of pi. We had a y value there of 3 pi. So 3 pi is over 9. Let's see, what else do we have here? We had some y values. Okay, what's 7 pi over 3? 7 pi divided by 3 plus 2 square roots of 3. That's like 10. Okay, so we need to have this go up to at least 10, 12 or so. So 1, 2, 3, 4, 5, 6. Actually, let me fix this. Let me space this out a little bit differently. Let's say like 2, 4, 6, 8, 10, and we'll say 12 up there. And we'll say -2, -4. Now, what are my x values here? I'm going to say like in terms of pi. That works. So let's do like pi. So pi over 2, 3 pi over 2. That's 2 pi. Anything above that we need? Oh, let's space those out a little more. I should have thought about that. We're only going to 2 pi, so let's put pi right there. 2 pi right there. 3 pi over 2 and pi over 2. All right. Now let's plot some of these points. So we have a y-intercept right there. Now where is a max and where is a min? Okay, we have a relative max at 7 pi over 6. Now 7 pi over 6 is a little bit past pi. In fact, it's pi over 6 past pi. So we have a point above here where we're going to have a relative maximum. Okay, so let's see. What was that? It was 7 pi over 3 plus 2 square roots of 3. So this y value right here is approximately 10.8. So we have this point right here. It's 7 pi over 6, and then approximately 10.8. So maybe about right there. And that's going to be a relative max. So relative max. Okay? Now what do we have here? We have 11 pi over 6. We have a relative minimum. So what's the approximate y value there? Well, it's 11 pi divided by 3 minus 2 square roots of 3. So that is an 8 approximately. So we have 11 pi over 6 comma 8 approximately. Now 11 pi over 6 is essentially pi over 6 less than 2. So it's a point x value like right over here. And the y value is right about 8. So maybe about like that. So that is a relative minimum. Now it might be also helpful to see what is f of 2 pi. Where does this end? Does it end? It's a relative minimum, so it has to curve and go back up. So where does what is f of 2 pi? Well, what's cosine of 2 pi? Cosine of 2 pi is 1. So we have 2 times 2 pi. So that's 4 pi minus 4. 4 pi minus 4. So 8.56. So the y value there was approximately 8. So we're going to get approximately 1 unit above, so that we're counting by 2's over here. So about halfway between 8 and 10. Not 1 unit, 8.5, so half a unit, so just barely above. Something like that. So that was 2 pi comma f of 2 pi, which is 4 pi minus 4. That's just the end point of my interval is all that is. Now let's see what's going on here. We're told that we are increasing to start with. We're increasing to 7 pi over 6. Okay, so we're starting at our x equals 0. We're increasing until we get to 7 pi over 6. then we're decreasing until we get to this point, then we're increasing after that. So we're going to have, let me just draw the general shape here, then we'll talk about concavity. Generally like this. Increasing, decreasing, increasing. All right, now let's think about how that affects concavity. Okay, we are concave up, okay, from 0 to pi over 2. So we have to be like curving upwards until we are right at pi over 2. So upwards curvature until we're above pi over 2. Okay, but then at pi over 2, we switch to concave down. So maybe something like this. So you see here, I'm concave up, and what is the coordinates of that point? Actually, it should be higher, because there's an inflection point at pi over 2, pi. Oh, no, pi, okay. So pi is about 3. So that's inflection. Because we switched from concave up over here, we're curving upwards, bending upward, to concave down. Now we're going to be concave down until we get to 3 pi over 2. So we're still increasing, concave down, but now we're decreasing and concave down. And now where's this next inflection point? It's at 3 pi. 3 pi is about 9.4. So now we have to switch. Now we have to switch from concave down to concave up, hit our relative minimums, and then we end right, or not relative minimums, hit our relative minimum, and then we end right there. So we are concave up to the left there. We're concave down in the middle here, and we're concave up over there. We are increasing from 0 to 7 pi over 6, which is until right there. We're then decreasing till we get to 11 pi over 6, and then we're increasing after that. So there you go. Without graph paper, I can be a little neater when I'm not using this tablet thing, but that's about what's going to happen. Okay, so there is a complete graph. We looked at inflection, we looked at relative minimums and maximums, we looked at concavity, we found the y-intercept. I decided to forego the x-intercepts because I knew they would be kind of tough to come by because of the original equation, but there's going to be an x-intercept somewhere right in there. I didn't really worry about that. That's no big deal for this time. But that is how we're going to graph trig equations. Sometimes you have to use identities. Sometimes, like this case, we got away without identities. And that's how we're going to go about most trig functions. Again, we'll have a restricted domain. Now, let's look at another example. So we've done a trig example. We've done a nice polynomial example. Now let's maybe do a rational example. Okay? So something that has asymptotes involved. All right, so let's look at the rational function f of x equals 2 times x squared minus 9 over x squared minus 4. Okay? Now remember, the thing that you want to just immediately take notice of is the domain. Okay? When you have a rational function, especially, polynomials have a nice domain. Trig functions usually have nice domains, but rational functions a lot of times have domains with restrictions, because here clearly we could say the domain is all real numbers except for x equals plus or minus 2. Because at plus or minus 2, the denominator is 0. Okay, and that's undefined. Now, immediately you should also say to yourself, are those two values also asymptotes. Now remember, the way an asymptote occurs is if the denominator is a 0 at a point and the numerator is not 0. So ask yourself, is the denominator 0 when x equals 2? Is the numerator also 0? And I think the answer is clearly no. If the numerator is 2, if x equals 2, you have 2 squared minus 9 would be 4 minus 9, so you'd have negative 5 times 2. So the numerator would be non-zero. So since the numerator is not 0, when the denominator is 0 at 2 and negative 2, that means that we have vertical asymptotes at x equal plus or minus 2. So that's something you really want to pay attention to closely when you have a rational function. Okay, where is the denominator 0 and is the numerator 0 at those same x values? Now, after we recognize that stuff, let's consider the derivatives. Now, I'm actually going to rewrite this. I think I would rather rewrite this as f of x equals 2x squared minus 18 over x squared minus 4. I think for the sake of derivatives, I'll do that. I'm not sure if it'll end up making it worse or easy, but I think it'll be easier to just go ahead and expand the numerator. Okay? Now, let's look at f prime first. That's usually the first step. F prime of x equals, okay, this is a quotient rule. Okay, so this is going to take a little work. We know it's going to be the denominator squared on the bottom, so x squared minus 4 squared. Now, as far as the numerator, that's going to take a little work. So it's the derivative of the top. Okay, the derivative of 2x squared is 4x. The derivative of negative 18 is 0. So the derivative of the entire top is 4x. So the derivative of the top times the bottom, x squared minus 4, minus the derivative of the bottom, which is 2x, times the top, which is 2x squared minus 18. Okay, now we need to simplify that. So the derivatives on this one are going to be harder than the previous ones. So f prime of x equals, let's see here. I guess we just need to expand the numerator, collect like terms, and see what happens. So that's going to be 4x cubed. Then we have minus 16x. Okay, then we're going to have minus 4x cubed. Okay, that's nice. Minus 4x cubed. Then we're going to have plus 36x, it looks like. Okay, let's double check that. 4x cubed minus 16x minus 4x cubed. Then we have plus 36x. Okay? So simplifying this, we're going to get f prime of x equals, okay, we have that x squared minus 4 squared on the denominator. Now the x cubes add to 0. Now we have 36x minus 16x, so I guess that's just 20x. So there's f prime. Now while we're in the mood of taking derivatives, let's just go ahead and find f double prime. Okay, this is going to be, again, a quotient rule. We know that the bottom is going to be the original, which is x minus 4 squared, but then we're going to square it again. That's what the quotient rule says. So you're going to take the derivative of the top, that's 20, times the bottom, x squared minus 4 squared, minus the derivative of the bottom. Okay, that's a chain rule. Okay, so it's the derivative of the outside function, which is 2x. The outside function is 2x, or excuse me, x squared, which the derivative is 2x. But we evaluate 2x at our inside function, which is x squared minus 4. raised to the first power there. But then we multiply by the derivative of the inside function, which is 2x. Now that right there, that is just the derivative of the bottom. The quotient rule says you take the derivative of the top times the bottom minus the derivative of the bottom times the top. So the top was that 20x. And then, of course, you divide by the bottom function squared. The original bottom function was this. We square it and get so. Okay, that's going to take a little bit of work, it looks like. First of all, let's notice what do you have here. We have an x squared minus 4 factor here, and an x squared, or we have 2 of them here. We have 1 here. Let's factor out an x squared minus 4. That'll help us a little bit. Now, what is on the bottom? What's x squared minus 4 squared? Well, that's x squared minus 4. Now, if you square something and then square it again, it's to the 4th power. You multiply the exponents. So let's see here. Let's factor out an x squared minus 4. Now, if we do that, we'll be left with what? A 20 times x squared minus 4 there. We'll then be left, let me fix that, make sure I can read my handwriting later on. That's a 20 times x squared minus 4 minus 2 times 2x times 20x. Now, why did I factor that out? I didn't have to. I could have foiled and collected a whole bunch of like terms, but actually I should have done what I just did there because it's going to make it would be hard to get back to that point because now I can cancel off this, and I can make that into a 4 to a 3. I cancel off one factor of x squared minus 4. Okay, lots of work with these derivatives, much more than we've seen thus far today. That's f double prime. So let's see, is it going to take, how many more steps is it going to take us here? So we have on the denominator x squared minus 4 cubed now. All right, let's see here. That's 20x squared. I'm distributing 20x squared minus 80. Minus, okay, what's this going on here? That is, okay, that's negative 4x times 20x. So negative 4 times 20, I suppose, is negative 80x. Okay, no, 80x squared rather. It's x and x. So minus 80x squared. 4x times 20x and a negative sign out front. Yeah. Okay. Alrighty. So let's see here. Need more and more room. I'd forgotten, since I have done this last, how long this derivative took. X squared minus 4 cubed. Now let's see here. We have 20x squared minus 80x squared. So that's minus 60x squared minus 80. Okay. Let's see here. Let's factor out. Let's do one last kind of cleaning up. We could say that f double prime of x, let's factor out a negative 20 on that numerator. That would leave us with a 3x squared, minus 4. X squared minus 4 cubed stays the same on the bottom. Okay? Oh, you know what? I factored out a negative 20. That's a plus. Sorry about that. So let's see, negative 20 times 3x squared plus 4 over the bottom as is. Yeah, okay. So just to recap here, those derivatives took a while to do. That's where we started. First derivative is in purple. That's not so bad. Second derivative took a little more work. Now, let's go back to the first derivative now that we have done all of our derivatives, and let's find our critical points. Now, I wanted to do one with asymptotes, a rational function, because of how the critical points play out. Alright, critical points are points for which the first derivative is 0. It's like we say f prime of x equals 0. Values of x, let's make that true. or values where the first derivative does not exist. But very important, both of those situations, those x values have to be in the domain of the original function. So if you're looking at f prime here, clearly f prime is not differentiable at positive 2 and negative 2 because f prime does not exist at negative 2 and positive 2. Okay, so we say that f prime, since f prime does not exist at negative 2 and positive 2, that the function is not differentiable at negative 2 and positive 2. So those could be potentially critical points, but a critical point has to be in the domain of the original function. And as we've already discussed, negative 2 and positive 2 are not in the domain of f. So they're not critical points. Okay? So let's solve this equation here and see what happens. So we have 20x over x squared minus 4 squared equals 0. Now here's the key that you got to realize. And I know we've talked about this in previous discussions, in previous lectures. The only way for this left-hand side to equal 0 is if the numerator is 0. So I can essentially say, I'll just solve this easier equation. Let's just solve instead 20x equals 0. Because that is the only way for this left-hand side to equal 0. Because it doesn't matter if the denominator is 0, that's a bad thing. That can't happen. Okay, there's asymptotes at negative 2 and positive 2. So all we have to do to solve this equation here, f prime of x equals 0, is to set the numerator equal to 0. And you can always do that when trying to solve a rational equation like this, equals 0. Okay, equal another number, different story. But equals 0, you can always do this little trick. And clearly the only answer to that is x equals 0. So we only have one critical point, x equals 0. So that means we can only have either a max or a min occur there. We only have one critical point, so we're only going to have one extreme value. Now, we only have one extreme value, but when I make my chart out for increasing and decreasing behavior, here's the thing. You have to include the asymptotes when you're dividing up your real number line. Okay, so even though we only have one critical point, whenever we're looking at the number line to look at our increasing versus decreasing intervals, we have to consider those asymptotes. So there's my only critical point. But I know at negative 2 and positive 2 I have asymptotes. It's possible for increasing and decreasing behavior to change at asymptotes. It's not guaranteed, but it's possible. So we have to consider negative 2 and positive 2 when we're building this chart out. So let's see here. Intervals. We're going to have negative infinity to negative 2. We're going to have negative 2 to 0. Oh, I'm going to run out of room here. We're going to have 0 to 2. And then we're going to have 2 to positive infinity. Now we need test points. So let's pick like negative 3 lives over there. Let's say negative 1, positive 1, and 3. Now we're looking at sine of f prime. So let's see, f prime is over here. Now, what can you tell me about the denominator there? The denominator is a squared expression. If you square something, what's the result? It's always positive. So the denominator here is positive no matter what. So all we have to do is think to ourselves, what's the sign of the numerator? If you plug in a negative 3 for x, the sign of the numerator is going to be negative. It's going to be negative 60. So negative. If we plug in a negative 1, what's the sign of the numerator? It's negative. So notice there, increasing versus decreasing behavior did not change. It's possible that it could have changed, but it didn't. So that's why you have to include the asymptotes there. Okay, now let's look at plus 1. Okay, clearly if you have plus 1 times 20, you get 20, which is positive. And then 3 times 20 is 60, which is positive. So we are, as far as our results are concerned, we're not increasing. Our derivative is negative here. So the original function's decreasing, and then since it's positive here, increasing and increasing. So that's the first thing to talk about, is that we're decreasing from negative infinity to negative 2. Excuse me, from negative infinity to 2. I said that wrong again. We're decreasing from negative infinity to 0, and we're increasing from 0 to positive infinity. Okay? Now, where we have changed, now remember, when you are looking for maximum and minimums, they have to occur at critical points. So we're only considering where we change from decreasing to increasing, or vice versa, and that has to happen at a critical point. And notice, we're changing from decreasing to increasing at a critical point of 0, our only critical point. So 0 comma something is going to be a what? A relative minimum or maximum? Well, we're changing from decreasing to increasing. So our function's going like this. Decreasing, 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 and then increasing again. That's going to result in a relative minimum. Okay? So we have a relative min at 0 comma something. Now, how do we figure out what that is? Actually, that's kind of nice, because that's exactly how you find a y-intercept. So it looks like our relative minimum is a y-intercept. Because how do you find a y-intercept? You evaluate f of 0. You plug in a 0 for x. So what happens if we plug in a 0 for x? We have what? We have 0 squared minus 9 times 2, so that is negative 18. Negative 18 divided by 0 minus 4, so you have negative 18 over negative 4. You have 9 over 2. So the y-intercept, which is also our relative minimum, our only extrema, is 9/2, 4.5. All right, so there's a good start. Now we have to consider the second derivative and concavity inflection points. So let's scroll down here. All right, so there's f double prime. Let's set f double prime equal to 0 to solve to find possible inflection points. Okay, so f double prime, we're looking for possible inflection points. Okay, so possible inflection points are given by f double prime of x equaling 0, so the solution is this equation, or they're points for which the function is not twice differentiable. That means we're looking for points where the second derivative does not exist. Well, guess what? At negative 2 and positive 2, the second derivative does not exist. Okay, but what have we already discussed? So it's almost like we want to make negative 2 and positive 2 a possible inflection points, but as we've said several times at this point, possible inflection points, possible or critical points as well, they have to be in the domain of the original function. And plus and minus 2 are not in the domain of the original function. So the only inflection points, possible inflection points we're going to get are going to be solutions to f double prime of x equals 0. So let's see here, that's negative 20 times 3x squared plus 4 divided by x squared minus 4 cubed equals 0. Now, just like we talked about a few moments ago, this left-hand side can only equal 0 if the numerator is 0. Okay? 0 divided by, we don't even care what the bottom is as long as it's not 0 at the same time. This can only be solved when the numerator is 0. So we can essentially solve this easier equation. Okay, so divide both sides by negative 20. We get 3x squared plus 4 equals 0. Now, if you're just blindly going along solving this, you won't notice it, but at this point, we've hit a roadblock. Now, you can see that roadblock clearly in just a sec. If we try to continue solving this quadratic, we'll have 3x squared equals negative 4, x squared equals negative 4/3, and then you'll use the square root property and say x equals plus or minus the square root of negative 4/3. But now we have this square root of a negative number, and that's a non-real solution. Specifically, we could say that x equals plus or minus, let's see, that would be 2 over the square root of 3i. Okay? But that means if there's no real solutions to this equation up here, f double prime x equals 0, that means there are no inflection points. Now, why should I recognize it at this step right here? At this step right here, I should recognize there's not going to be any solution because I'm taking 3 times some x squared. X squared is at the very least 0. If you square a negative number, you get a positive number. If you square a positive number, you get a positive number. If you square 0, you get 0. So at the very least, this left-hand side is 4. It can't get less than 4. So if you have the left-hand side is always 4 or bigger, you can never make it equal 0. So no solution. That means there are no inflection points. No inflection points. Okay? Now, it doesn't mean we can forget about concavity, but there are no inflection points. Okay? So, now, when we make out our table for concavity, there's no inflection points, but we do have to use our asymptotes. So if we had inflection points, possible inflection points, we would use those possible inflection points along with our asymptotes to divide the real number line. But we have no possible inflection points, so we're just going to use negative 2 and positive 2, our asymptotes. Because you have to consider the asymptotes when you're trying to figure out where the function is increasing or decreasing. All right, so let's build out our chart for concavity. So we're going to have our intervals. We're going to have negative infinity. It's negative 2. We're going to have negative 2 to positive 2. And we're going to have from 2 to infinity. Let's look at our test points. Let's see here. Let's pick a negative 3. Let's pick a 0. And let's pick 4 just to mix it up. We are looking at the sine of f double prime. Since we're considering the second derivative. So where is our second derivative? Okay. Let's see here. If we cube, let's think about this right here. If we cube negative 3, we get 9. 9 minus 4 is 5. 5 cubed is 125. So the denominator is positive. But if I plug in a negative 3 up here, I get negative 3 squared, which is 9. 9 times 3 plus 4, that's positive. A positive number times 20, which is a negative number, divided by a positive number, I get a negative result. Again, I'm not caring about the exact answer here. I'm just concerned with what the sign is. What happens when you plug a 0 in? If you plug a 0 in for x in the denominator, you get negative 4 cubed. That's negative 64. So the denominator is negative. What's the numerator? The numerator will also be negative. So you have a negative number divided by a negative number results in an overall positive number. What about if we plug in a 4? If you plug in a 4 on the bottom, you'll have 4 squared, which is 16. 16 minus 4 is 12. 12 cubed is a positive number. What about the numerator? Well, in the numerator, though, you'll have a positive number on this factor times negative 20, which will be negative on the numerator, with the positive denominator. So the quotient, the total, is negative. So what's our result or conclusion? Where f double prime is negative, we're concave down. Where f double prime is positive, we're concave up. Okay, so what have we done here? We have found concavity using the second derivative. By the way, we can verify this relative minimum right here using the second derivative. So we claim that we have a relative minimum at 0. What we've already found is the sign of f double prime is 0 in our chart right here. The second derivative test says if you take a critical point, in this case is 0, and you evaluate your critical point at the second derivative, which we just did, and the result is positive, then you have a relative minimum at that critical point, which is exactly what we said. So the second derivative test verifies the first derivative test. Those two things can never contradict each other. If you think they do, then you made a mistake somewhere. They can verify each other. That's why I typically like to do both, as long as I remember, so that we can double check ourselves. Make sure we got the right solution. Okay, so let's see. Do we need anything else here? We have increasing versus decreasing behavior. We have our extrema, the 1 point, our minimum. We have asymptotes. What about, horizontal asymptotes? That is, we need to look at the limit as x approaches infinity. So, okay, let's write our function down here. Let's get a little more space. Let's look at the end behavior. That is, we want to look at the limit as x increases without bound of f of x, which we said was 2x squared minus 18 over x squared minus 4. We also want to consider the limit as x decreases without bound. That is, goes off toward negative infinity of our function. Now, what do you remember about evaluating the limits at infinity of rational functions? Well, the technique was to consider the degree of the numerator and the degree of the denominator. If the degree of the numerator was equal to the degree of the denominator, then the limit was just the rational, ratio of the leading coefficients. So degree is 2 on the numerator, degree is 2 on the denominator. They're both squared. So if you square a negative number, or in this case we're squaring a positive number, the results are positive. So our limit is just 2 over 1 equals 2, because the degree of the top equals the degree of the bottom. Okay, what about on the limit as x decreases without bound? Same thing. We still have a rational function with a degree 2 numerator, a degree 2 denominator. So the limit is the ratio of the leading coefficients, which is 2. So that means we have a horizontal asymptote. At, not x, at y equals 2. So we have vertical asymptotes, 2 of them. We have one horizontal asymptote. We have increasing versus decreasing. We have concavity. We have one relative extrema. Anything else we need? We could get x-intercepts. Let's do that. So here's our function down here. How do you find x-intercepts? Well, you set f of x equal to 0 and solve. Okay? If you're trying to set f of x equal to 0, that's how you find x-intercepts always. So we have 2x squared minus 18 over x squared minus 4 equals 0. Again, that same trick applies. the left-hand side is only 0 when the numerator is 0. So we need to solve not this entire thing looks complicated. We can actually translate that into 2x squared minus 18 equals 0 and solve that. Now that's a lot easier because we can divide both sides by 2 and get x squared minus 9 equals 0, which then we know easily solves to x equals plus or minus 3. So there are x intercepts, plus and minus 3. So I think we have plenty enough information to go ahead and put this all together. Let's see, do I have any room up here? Sure, I think I have enough room here. Let's see. Let's have some orange axes this time. Alright, let's put our asymptotes first. We have asymptotes. Well, actually, let's put some scale there. Let's see. Our scale isn't anything too crazy. So where were our asymptotes? They were 2 and negative 2. So 1, 2, we'll count like so. Alright, let's put our asymptotes in pink. We had negative 2 and positive 2. Where are our asymptotes? Oh, too far. Yes, negative 2 and positive 2 are our asymptotes. So let's put those in. I'll just make them as dotted lines. What was our horizontal asymptote? We found that our horizontal asymptote was y equals 2. Now, if you remember from college algebra, a horizontal asymptote of a rational function cannot be crossed. A horizontal asymptote in general can be crossed, but not a rational function. This is a rational function here. So we can't cross any of these dotted pink lines. Now let's put in some points we know about. We know that we have a y-intercept at 0, 9 halves. Okay? Right there, 0, 9 halves, and that's a relative minimum. Oh, I should have made the scale and the y-axis a little bit smaller. Let's count by 2's here on the y-axis. 2, 4, 6. And we'll count by 1's on the x-axis. 2, since we already drew those asymptotes. Okay? So that's going to be negative 2, negative 4, and negative 6. All right. So let's put in our relative minimum, which is also our y-intercept. It's 0, 4.5. So it's about right there. Oh, let's make that a different color. That's a little more contrast. What about this? Yeah. Okay. So there's the minimum, or it's a local or relative minimum. Not the minimum. That would be the absolute smallest point. And there's not going to be an absolute smallest point on this graph. Okay, x-intercepts we found were plus or minus 3. So let's go back up here. X-intercepts and x-intercepts. Now, let's consider how asymptotes work in conjunction with our concavity and increasing versus decreasing behavior. So we have a vertical asymptote, which means we're going to be approaching this asymptote in some form or fashion. Now, what are we doing? Are we increasing or decreasing? Well, okay, we have to cross that intercept right there, and we know we're decreasing. So we're decreasing from negative infinity to negative 2. We have to hit our x-intercept, and we have to approach this asymptote. So it's going to have to be something like this. Okay? We know we have an x-intercept here. We have to hit that point. We're decreasing, and we have this vertical asymptote we're up against, and this horizontal asymptote we're up against. So that's about the only option there. Now, what about here in the middle? We know we're decreasing from negative 2 to 0. So we're decreasing over here, and this is a relative minimum. So we're decreasing toward it. Now, what about concavity here in the middle? And let's just verify here. We're concave down from negative infinity to negative 2. And yes, that's concave down right there. We're bending, opening downward, concave down. But we are concave up from negative 2 to positive 2. So we're concave up here in the middle. We're decreasing from negative 2 to 0, and we're increasing from 0 to 2. So that makes sense. So we're like this. It's like a parabola here in the middle. Oh, that's not very pretty. Let's just do this. Okay, again, we have asymptotic behavior. So we're approaching this asymptote on the left, and we're approaching this asymptote on the right. Now, I should be clear. We never go vertical, but we're approaching the asymptote on the left and the right. We're decreasing from negative 2 to 0, and we're increasing from 0 to 2. And we're concave up between negative 2 and positive 2. Now, let's see what happens after 2. From 2 to positive infinity, we are increasing. We're also concave down. So kind of like a reflection of what's happening over here. We know we have to cross this point right here. We're increasing towards this asymptote. And so really, the only options for us are that. And there you go. We have our intercepts. We have our extrema. We only have one. We have an extremum. We have one. It's a local minimum. We have our asymptotes. And there we go. We have our y-intercept was also our local minimum. And that's your complete graph. Again, rational functions are kind of tedious because of the derivatives. We had to spend so much time finding the derivatives. There's our original f of x here. I then rewrote it distributed on the numerator. The first derivative wasn't much to it, but the second derivative took several steps. And then we had to find increasing versus decreasing behavior. We only found one relative minimum, no maximums. And clearly from the picture, we see no maximums. Okay, no relative maximums, one relative minimum. And we see here that there's no inflection points because inflection changes at asymptotes. That's possible. So inflection changed from not inflection, concavity. Concavity changed from down over here to up here in the middle to down over here, but it changed at those two asymptotes. Sometimes your concavity changes at asymptotes, at other times it doesn't. It's not guaranteed to change, but sometimes it does. So you really have to do a full analysis to really see what the complete graph looks like. Okay? Of course, if we had graph paper, it would look a little better, but I think that's pretty good for using this tablet that's hard to write with, and we hit the high points, asymptotes, intercepts, extrema, inflection points, which there were none here. You got to hit the high points to get a good idea of what's going on. Okay, and of course we have the end behavior dictated by this horizontal asymptote at y equaled at y equals 2. What did I do here? After all of that, I realized I put my horizontal asymptote at 4. After all of that, I don't know what happened there. Where did I get 4 from? The horizontal asymptote goes at 2. All right, I got to do a little racing. here. I can't leave it like this. All right, let's erase this. It's not too bad of a fix. Not too bad. We can salvage this. Let's get rid of that. Okay. Let's get rid of that and this. I'm not sure why I did what I did there. If you were confused, I apologize, because that horizontal asymptote was supposed to be at 2. For some reason, I said 4, and I'm really not sure why. I don't know if I glanced down and saw something wrong, but 1, 2, 3, and I know I changed. That's what it was. Okay, I changed the axis, the scale on the vertical axis because of my y-intercept, but then I wasn't paying attention whenever I graphed the. The asymptote. So now that I've drawn the asymptote and drawn the entire thing, I'm just going to have to move this up. So I remember I'm really sorry about that. I wasn't paying close enough attention there. So remember, our intercept for the y-intercept was 0 9/2, which was right there. So this way, I just need to, I'm completely out of room here, but we have that. Again, we're still between our asymptotes. So let me extend those asymptotes like so. Again, I'm really sorry about that, guys. I should have been paying more attention there. Sometimes I don't pay enough attention and get carried away here. So let me fix this little arrow here, since my local minimum now is way up here. There we go. So now we're all fixed. If you've been confused that entire time, I make mistakes just like everybody does. No big deal. I'll put a little note. I'll put a little note when I make a mistake. Say, hey, I fix this later. Just don't worry about it. Okay? All right, so that's a rational function. Now, I'm going to take a little break here because I've been working on this for a while. I think I might add one more example, but we'll see. We'll see how I feel. Maybe we'll just go ahead and publish this video, but I might take a little break and then I might make one more example. These take a while. There's no easy trick to it. You just have to practice and get all of these techniques down. So we'll see. Maybe I'll do one more example before I publish the video out. But this is how they all work. You got to analyze the first derivative, analyze the second derivative, find x-intercepts, find y-intercepts, find the limits at infinity to figure out the end behavior, finding horizontal asymptotes in the process, and that's how it all plays out. So practice is key. All right, let me take a little break, and maybe I'll come back and work one more example.
All right, now the last function, f of x equals, we have 2 times x to the 5/3 and minus 5 times x to the 4/3. Now remember, our general strategy here is find the first derivative, find the second derivative, and then finding critical points, inflection, limits at infinity, all of that stuff. So let's just hop right in with the derivatives. So let's see here, f prime to start with, f prime of x, well, okay, this is just 2 power rules. So you bring the original power out front. So we have a 2 there already, so it's going to be 10/3 now, because 2 times 5/3 is 10/3, times x, and we reduce this power by 1. So if you do 5/3 minus 1, well, I think you get 2/3. Minus, okay, we have 5, then if the power rule says bring a 4/3 out front, so that's going to be minus 20/3 times x. Now what's 4/3 minus 1? I think that's 1/3. Okay. Now that's f prime. Any reason to simplify that currently? Oh, I mean, you could factor out a 3 for sure. You could even factor out a 10. You could factor out a 1/3 and factor out a 10, so 10/3. I'll leave that alone for the time being. Let's just go ahead and find f double prime. So let's look at f double prime now. So we're just taking the derivative of the derivative. Now we're going to bring that 2/3 out front and multiply by 10/3. So that's going to give us, oh, let's see here, that's what, 20 over 9 times x. Now we reduce 2/3 by 1, so that gives us negative 1/3, I believe. Negative 1/3. Minus, okay, let's bring that 1/3 out front. So we get another 20 over 9 times x. Now reduce 1/3 by 1, that gives us negative 2/3. So if that confused you, those few derivatives, make sure to touch up on how to take derivatives with fractional exponents for sure. When you have a power rule with fractional exponents. We don't deal with these every day, but we certainly deal with the power rule every day. Let's simplify both of these derivatives because we're going to have to set them equal to 0 and solve anyway. So let's just go ahead and simplify them. If we factor this, we could certainly factor out a 20 over 9 for sure. And I think we can actually also factor out an x to the negative 1/3. Because they both have that in common. Now if I factor out, that's essentially factoring the entire thing out here. So I'm just left with a 1. Oh, sorry. A 1. Okay. And then what about if I factor out? Oh, you know what? That's interesting. What about if instead I factor out what if instead I factor out a 2/3 instead, or a negative 2/3 instead of that positive 1/3? What if that works out better? What if I did this? If I factored out a 20 over 9 times x to the negative 2/3, what would be left in this first step? Well, I think that would be an x to the positive 1/3, because remember, if we were going to FOIL this, we would need to multiply these two variable expressions, in which case we would add the exponents, and negative 2/3 plus 1/3 gives us that negative 1/3. Okay? And then now we can say minus 1. And that's nice there because now that's factored very nicely for us, and we can easily solve this once we start trying to find inflection and concavity and such. Now let's factor this f prime. Now what can we factor out here? We could certainly factor, a 10 and a 3 for sure, a 10/3 out. Now anything else we can factor out? Yeah, we can factor out an x to the 1/3 there. And what's left over inside? Well, I think that's going to be an x to the 1/3 power. And then minus, what would be left over here? So just minus 2, I suppose it is. Okay? Because we have 20 over 3. I factored out a 10 over 3. So if we distributed back, we would certainly get a negative 20 over 3 there. Now the reason I just did both of those is because that will help us solve to find critical points and find inflection points and so forth when we start doing that in just a moment. So let's start with the first derivative. So this blue line here, the first derivative we need to set f prime of x equal to 0 and solve. Now I factor this, so this should be solved pretty easily. 10 over 3 times x to the 1/3, and then we have times x to the negative 1/3 minus 2. Alright, Oh, I said negative 1/3. That is not a negative 1/3. That is a positive 1/3 minus 2 equals 0. Now, let's see here. Now, that clearly, or if we want to solve this here, clearly we have it factored already. So we can say, well, first of all, we could multiply both sides by 3/10. And that would just give us that we need to solve x to the 1/3 power. 1/3 power equals 0, or x to the 1/3 power minus 2 equals 0. Now, what's the only answer here? The only answer here is that x equals 0. So x equals 0 looks like it's going to be a critical point. And let's see here. That says we're solving for, we need to solve x to the 1/3 equals 2, so we cube both sides and we get x equals 8. Okay? Because 2 cubed is 8. Okay? So there's our two critical points. Now, of course, we need to double check to make sure those two critical points are in the domain of the original function. Now, looking here at the domain of the original, we could certainly plug in a 0, no problems. We could certainly plug in an 8, no problems. So those, both of those critical points, or both of those values for x, are critical points because they are in the domain of the original function, and they make the first derivative 0. Now, other critical points could be points for which the first derivative is not defined, but it looks like this first derivative is defined for all real numbers, so there's no issue there. Now, so there's our two critical points. Let's conduct the first derivative test and figure out if these are maximums or minimums, or what's going on at these two values. Okay, so the first derivative test, that's when we make a chart and we consider increasing and decreasing behavior of the function. Now let's think about our test intervals. Now I didn't talk about domain of the original function, but it looks like the domain of this original function is all real numbers. We are taking a number, we're raising it to the 5th power, then taking the 3rd root. No issues there, because we can always take a 3rd root of a number. Here we're taking a number, raising it to the 4th power, then taking a 3rd root. Yeah, so there's no problem there. So the domain of f is all real numbers. So I'm talking about the entire real number line. Plot my two critical values, and clearly we have 3 test intervals to worry about when talking about increasing versus decreasing behavior. So let's build out our chart. Intervals. So let's see here. Going to be 3 of them. We have -infinity to 0. We then have a 0 to 8. Oh, I guess a sideways infinity is about like an 8. And then we have from 8 to infinity. Okay? Now let's pick test points. So let's see here. Oh, let's do -1, let's do +1, and let's just do 9. Now we are looking at the sign of f prime when we are talking about the increasing versus decreasing behavior. Now where is f prime? It's up here. Let's see here. If we take -1 and evaluate f prime of -1, well, the cubed root of a negative number is negative. Okay, so we're gonna have a negative number here. The cube root of a negative number is negative, so it's negative minus negative. So we're gonna have a negative number times a negative number, which results in a positive number. Remember, I don't really care about the exact number. I just care about the sign of f prime. Now, what about at 1? Okay, well, this right here, this factor would be positive because the cube root of a positive number is a positive number. But here we would have the cube root of 1, which is just 1 minus 2. So you have negative 1 times a positive number over here, which results in a negative. Then what about 9? The cube root of a positive number is positive. Then the cube root of 9, so I guess the question is the cube root of 9 less than 2? Because if it is, then a number less than 2 minus 2 is negative, and a negative times a positive is negative. But let's see here. What is the cubed root of 9? So 9 raised to the 1/3 power. Oh, that is barely bigger than 2. It's 2.008. 2.08 minus 2, so that's positive. So this is positive. Now what does that mean? That means we are increasing here, decreasing here, and increasing here. Now what does that tell us about maximums and minimums? That tells me that I have a local max anywhere that I change from increasing to decreasing at a critical point. So that means at 0 I change from increasing to decreasing. So at 0 comma something I have a local max. Now what about a local min? Okay, I'm changing from decreasing to increasing at 8, which is a critical point. So at 8 comma something, I have a local minimum. Now let's figure out those y values by going to the original function f. Clearly, if I plug in a 0, f of 0 is 0. That's easy. Now 8 is a little more difficult. Let's see here. I'm actually going to use my calculator here. We'll see if f of 8 ends up being a nice number. So let's see, 2 times 8 raised to the 5/3 power minus 5 times 8 raised to the 4/3 power. Negative 16. You know, we can do those by hand, but it's not fun. So I'll just use my calculator here, since that we're not, the goal here is to not use a graphing calculator, but any old calculator can do this right here. Any old scientific calculator can do that. So again, I'm not going to allow myself to use a graphing calculator, but I'm not worried about using one for arithmetic. So there's the first thing we need to worry, or the first goal here. We found local maximums and minimums, and we found the intervals of increasing or decreasing. We can get a pretty good picture with just that information. But now let's look at the second derivative. Okay, because the second derivative is going to give us concavity. Now let's see here. F double prime, this gives us possible inflection points when we set f double prime of x equal to 0. So here's f double prime over there, the factored version. So 20 over 9, x to the negative 2/3 power times x to the negative 1/3 power minus 1. Oh, I did that again. X to the positive 1/3 power minus 1 equals 0. Oh, you know what? I should probably rewrite this in fractional form, because this actually is, what is x raised to the negative 2/3? That could be rewritten like this. 20 over 9 x to the 2/3 power. Now why does that make a difference? Well, that makes a difference because you can clearly see that this function is not differentiable when x equals 0, because that would produce a 0 on the denominator, which is no good. So 0, it's not all the time that we get a critical point that is due to a function or to a derivative not being, I just said critical point. These are inflection points. It's not every day that we get an inflection point due to a second derivative not being defined, but that does happen. Okay, so the second derivative is not defined at x equals 0, which is a going to give us a possible inflection point at x equals 0. So x equals 0. Now, it's not a solution to this equation, but it is a possible inflection point because it's not twice differentiable. So when the second derivative does not exist at a point, we say it is not twice differentiable at that point. Okay, so x equals 0 is a possible inflection point, although it's not a solution to that equation. So I just want to be clear there. I say x equals 0 because it's a possible inflection point, not because it's a solution to this equation. Now, what is the solution to this equation? I think x equals 1. If we set this factor equal to 0 and solve, I think x equals 1 is another possibility. Okay, so there we are. X equals 0 and x equals 1 are possible points of inflection. Now, again, we need to make sure these are in the domain of the original function. And I think we said that the domain of the original function was 0 and it was all real numbers. So yes, I think that 0 and 1 certainly are there. But you know what? I went to all that trouble to talk about this. We already know that 0 is a local maximum. Well, I guess it could be. You don't know. I don't know what this graph looks like. That it could be an inflection point too. So let's see what happens here. We already know that 0 is a local maximum. Could it be a point of inflection as well? Interesting question. Well, let's build out our chart and see if it's a point of inflection. Who knows? Let's see here. We have. Let's see. Let's do this Kelly green color. So we have these 2 points for our possible points of inflection. The domain of f was all real numbers, so let's divide up the domain of f like so. So we want to do concavity now. So we have 3 intervals according to these divisions. We have negative infinity to 0. We have 0 to 1. And then we have 1 to infinity. Oh, we need some test points. Oh, let's see, negative 1, that works. Oh, I guess we're going to have to do like a fraction there, 1/2. And let's just do 2. So now we're looking at the sine of f double prime. Now where is f double prime? That's right here. So what happens if we plug in a negative 1? Okay, well, if we plug in a negative 1, the cubed root of a negative 1 is a negative. So this is a negative minus a negative is a negative. Okay, if you take the negative 2/3 power of negative 1, that's a positive result. So a positive times a negative is a negative result. Okay. Now what about in the middle here from 0 to 1? Now from 0 to 1, what is happening? If we plug in a 1/2, okay, the cube root of a 1/2 is still a positive number, but it's going to be a pretty small number. So let's see exactly. What is the cube root of 1/2? It's about 0.79. So 0.79 minus 1, that is a negative number. But over here, then that is going to be if you look at the 1/2 squared, then the cube root, that's still a positive number. You then take the reciprocal, it's still a positive number. So you have positive times positive, positive times negative rather, and we are still concave downward. Okay, so it turns out that 0 is not an inflection point because it is concave down on both sides of 0, but we already knew that 0 was a local maximum. Okay, so that makes sense. Okay, so we're not changing concavity there, but you never know. 0 might be a weird point here. That's why I wasn't, I didn't want to speculate. Plus, it's really late at night, and my, I don't think as clearly late at night as I might in the middle of the day. So I didn't want to speculate without thinking about it too much. Now, what about 2? If we look at f double prime of 2, well, clearly, I don't know. What is the third root of 2? I guess that makes a difference. Let's see. Math. Third root of 2 is 1.2. So 1.2 minus 1, that's a positive factor. That's positive. So I think that is a positive result. So that tells me that we're going to be concave up over here. So we're going to be concave down, down, and then up. So we do have an inflection point then here at 1, because we are changing from we are changing from concave down to concave up at x equals 1, so 1 comma something is an inflection point. So inflection, 1 comma what now? Well, okay, the 1 to the 5th power to the third root is just 1. So you have 2, and then the same thing, the 4/3 power is just 1, so 2 minus 5 is -3. Okay, now what is the last things we have not done yet? We've done first derivative analysis, we've done second derivative analysis. Oh, what about end behavior? What about end behavior? So let's look at the limits. Now let's remind ourselves what f of x is, and let's write down these limits. We want to consider the limit as x approaches infinity of f of x, and we want to consider actually, let me write out exactly what f of x is, then we can scroll down a little bit. 2 times x to the 5/3 minus 5 times x to the 4/3. And then we also need to look at the limit as x decreases without bound, that is, approaches negative infinity, of 2x to the 5/3 minus 5x to the 4/3. Now let's think about this. If x gets really, really, really big in the positive direction, we're going to raise it to the 5th power, then take the third root. It's still just getting bigger. But then we're going to subtract off x to the 4th power and to the third root. Now, I think that even though we're subtracting, I think that this is going to increase a lot faster than this is going to increase, because we're subtracting they're both the third root, so we can kind of ignore the third root part. The question is, and I think it's clear here, is if you ignore the 1/3, so that's a third root. The 5th power is growing at a faster rate than the 4th power. So this is, even though we're subtracting off this 4th power, it's still going to go to positive infinity. Think about 10 to the 5th and 10 to the 4th. 10 to the 5th is 100,000. 10 to the 4th is 10,000. 100,000 is a lot bigger than 10,000. Okay? So it's growing, this factor is growing a lot faster than this factor, so it's going off towards positive infinity. Now what about if we are talking about x is getting really, really big in the negative direction? Now here's the thing, if you take a power, a number x, and you raise it to the 5th power, well, that's an odd power, and then you take an odd root, this is going to be a negative solution here. And then if we take a negative number right here and plug it in, well, you raise to the fourth power makes it positive. Take the third root, it's still positive. But then you have a positive times a negative 5, so both of these are negative. So as x gets really, really big in the negative direction, this is getting really, really, really negative super fast because both of these factors end up being negative. So this is getting really, really negative in a really fast way because these are both working together. Like here, you have this is getting big and this is getting big, but we're subtracting it off. So like this right here, this factor is counteracting this this term rather. But it's still going towards positive infinity. But here, it's like they're both working together to get negative really fast. This is dropping super fast. Now, am I missing anything? We have our end behavior. So this is our right hand end behavior. This is our left hand end behavior. And I think we can start putting all the pieces together here. Now I'm gonna have to scroll down to get some room here. I'll have to scroll back up to get all of the information we need. But let's see here. We have a graph. Now, what points do we know we're on our graph? I remember that 0, 0 was a maximum, I believe. Oh, let's get some scale here. Let's see here. Let's just space out like so. Oh, the one thing we have not done yet. Now we know certainly our y-intercept is 0 because I think we said 0, 0 was a maximum. But we might have more x-intercepts, so let's see about those before I start graphing. Now here is our original function. To find x-intercepts, we just set that original function equal to 0 and solve. So we could say like 2x to the 5 thirds minus 5. Oh, let me fix this. 2x to the 5 thirds minus 5x to the 4 thirds equals 0. Now how might we do this? Oh, we should factor it, that's why. Factor out the greatest common term. Now there's no coefficients in common, but let's factor out x to the what power? If we factor out x to the 4 thirds, we would have 2 times x to the 1 third minus 5. Okay? Factor out the greatest common term, x to the 4 thirds, and yeah, I think that's good. You're left with just a 5 over here, and you're left with a 1 third. Imagine if you distribute it back, you would get 2x to the 5 thirds, since you would add the exponents. I think that works out. So by the zero factor theorem, we know that either x equals 0, so that's an intercept. We already knew that. It's actually a relative maximum. But we also need to solve 2x to the 1 third minus 5 equals 0. So we could say that, let's see here, x to the 1 third equals, let's see, that would be 5 over 2. So that means if we need to cube both sides to solve, x equals 125, which is 5 cubed, over 8, which is 2 cubed. So there is our other x-intercept. We have 2. So we have an x-intercept, which we already knew about, and x-intercept. Now, what is 125 over 8 approximately? That is approximately 15. Oh, so I need to count by something higher over here than just ones. So let's count by, we count by 4s, about 3s. If we count by 3s, 3, 6, 9, 12, 15, 18, that works. Now, what about our y values? What were our smallest y values? Oh, we had a negative 16, so we probably need to do the same thing on the y-axis. Oh, we probably need to go even further. Let's see, how much space do we have? We do 3, 6, 9, 12. I guess we can do 3s again. So negative 3, negative 6, negative 9, negative 12, negative 15, and negative 18. Now let's start plotting these points that we know about. We know that we have a 0, 0. Let me just double check. I think we said that was a maximum. Yep, local max. So that is a local max. Now where was our other, clearly it's also an x-intercept and a y-intercept. We know that we have a x-intercept at 125/8, which is almost between 15 and 16. So let's just say a little bit over 15, about right there. So that is nothing but an x-intercept. So to find that, all we did was a little bit of algebra. So there's 2 points. Now what about our local minimum? Where was that? 8, negative 16. So there's 6, there's 9, so 8 is almost about right there. And it's negative, negative 16. So about right there. Now that was a local minimum. So a local minimum. Now what else do we have here? Oh, let's talk about increasing and decreasing. And in behavior. We know that our in behavior to the left, we said it was getting really negative really fast. But then to the right, it was just getting big. Now, does that match up with our increasing and decreasing? Yes. We are increasing from negative infinity to 0, which matches up with in behavior going off towards negative infinity. Okay? So we're going to probably have something like this. It's getting really negative. It's increasing, so we're increasing from left to right. But we said that in behavior, the further you move away from the origin, the y values are getting negative really fast. Now what's the concavity like? We said that the concavity from negative infinity to 0 is down, so we need to have curvature, you know, like this. We're increasing, but we have concavity curvature like that. Now that was a local minimum. It's not going to be a cusp there. I thought it might be a cusp, but that was actually a local extrema, a local maximum that wasn't due to undefined, a non-differentiable point. So there's actually, it needs to be enough curvature to where there's a horizontal tangent line there. Okay, so we're going like this. Oh, we are going like this, getting really negative really fast. We're increasing, concave down, we hit a local maximum. Now what happens to the right of 0? To the right of 0, from 0 to 1, we're concave down. Okay, concave down, so it's like the tip of a parabola. And then from 0 to 1, so we're just for a second, we're still concave down, kind of like I've drawn here. So that's good. But then from 1 to infinity, we're concave up. So then we like bend and we're curvature, but we're still decreasing. We're decreasing all the way to this point here to our local minimum. But we switch. Now where's that point of inflection? That point of inflection was at 1, negative 3. So let's draw 1, negative 3. So about right there is inflection. So we go like this. We're still concave down. But then we change, and we're still decreasing, but we change to concave up. And we have to go to that local minimum, so like that. So see how if you just ignore, if you kind of like draw a vertical line right here, and you look to the left of that vertical line, you know, it's like we have a parabola, a downward opening parabola. But then if you look to the right, it's like we're concave up from there to positive infinity. So it's like we have to the right of that green dotted line, we have an opening upward parabola. That is concave up. Okay. Now let's make sure I got that right. We are increasing from 8 to infinity. Yep. We hit this local minimum, then we start increasing. So we're decreasing all between here, but we are concave down from 0 to 1, but from 1 to 8, we are from 1 to infinity, we're concave up. So everything to the left of this green dotted line, we're concave down, but to the right of that green dotted line, we're concave up. We have our inflection point, that was at 1, -3. We had a local minimum down here, that was at, what did we say, 8, -16? Yeah. 8, -16. We had that x-intercept, that was at 125 over 8, 0. Our local max was the origin, 0, 0. And that's, I think, everything. Our end behavior to the right was off towards positive infinity. To the left was down towards negative infinity. And there you go. I think that's about as good as we can do by hand. Graph paper would make it a little nicer. But there we go. So, just to recap, we've done an equation, a function with asymptotes. We've done a trig graph. Here we did a graph where, we had some odd-looking powers. All these are different. Practice, practice, practice. You got to practice these things, but the general idea is the same. Find the first derivative. Do everything you know about that first derivative. Do the second derivative, or find the second derivative. Do everything you know about that second derivative. And then find do a little bit of algebra. Find x-intercepts. Find the y-intercept. If there happens to be any symmetry, recognize that. No symmetry here, we don't have to worry about it. But just, combine everything that we have been talking about in Chapter 4 and put it all together. That's what we're doing here. So, I hope these examples have been helpful to you. Of course, just keep practicing, and if you need help, let me know. And remember, the goal here is graphing by hand. We don't want to rely on a graphing calculator. So I did all of these by hand. I used a calculator occasionally to do some arithmetic for me, but beyond that, I didn't use the graphing capabilities. So you'll have the option on your test to use a scientific calculator, but if you're in my class, for this particular test, you won't have a graphing calculator. So make sure you're not relying on a graphing calculator when you're working on these type of problems. So good luck. If you need help, just let me know. I'm always just an email away. Talk to you soon.